Alright, so let's discuss line integrals. There are different types of line integrals, and in this video I'll be talking about the DS type. Alright, so suppose you're given the parameterization of a curve C to be r of t is equal to x of t I plus y of t j, and t ranges between a and b. So if you sketch this parameterization at different values of t, you're gonna get different position vectors and so on. So if you trace all these position vectors, you're gonna get a curve C that follows these position vectors. So this curve here, C. Now suppose C is a wire with varying density. And the density depends on the location. This is density per unit length. So depending on where you are in the plane, the density of the wire changes. And you want to find the mass of the wire. So one way we can find the mass of the wire is if you take this wire here, break it into many small pieces, infinite number of small pieces, and let's say that every small piece has the length ds. Then we can say that for a small piece, the mass is equal to the density at this point times the length of the small piece, which means that the mass of the wire is equal to the integral along the curve C of the density times ds. Okay, so let's take a closer look at one of these small parts. So I took a small piece, it's called ds here. If this is ds, then this over here is dx, and this is dy. And we can say that ds is equal to the square root of dx squared plus dy squared. Now I'm going to take this and substitute it into this equation. Therefore, the mass of the wire is equal to the integral along the curve C, density, and instead of ds, I'm going to write square root of dx squared plus dy squared. Now, since this curve, the parameterization of this curve was in terms of t, we can write everything in this integral in terms of t to make the calculations easier. So the mass of the wire is equal to, now t ranged between a and b, so the limits of integration is going to be a and b, density x of t y of t times the square root of dx squared plus dy squared. But I'm gonna take dt squared as a common factor, so if I take dt squared as a common factor, it's gonna be dx divided by dt all squared plus dy divided by dt squared. Now I'm gonna take this dt squared out of the square root, so it's equal to the integral from a to b, density times the square root of dx dt squared plus dy dt squared. And if you take the dt squared out of the square root, you're gonna get dt. And at this point, it's much easier to integrate and find the mass of the wire. So let me give you the method and general formula for the ds type of line integrals. Okay, to integrate a continuous function over a curve C, the first step is to parameterize the curve, and the second step is to substitute this parameterization into the function and then multiply it by the square root of dx dt squared plus dy dt squared plus dz dt squared, and you integrate this whole thing with respect to t. Of course, if you're dealing with a two-dimensional function where you only have x and y, you can get rid of the z of t and the dz dt squared here. Some of the useful applications of the ds type of line integrals is to find the mass, the center of mass, and the moment of inertia.